This last lecture aims to understand how things like ChatGPT or DeepSeek have been trained. And they are a mixture with this reinforcement learning that we have seen so far and a human feedback. So this is more like ChatGPT. So let's say that we have a foundation model that tries to predict the next token in sentences. So the model knows a lot because it has seen many large amount of texts, but it is not particularly good at understanding human intentions. So our goal will be to train or to retrain or to put something after that model so that it can follow instructions, so summarization or question and answering, or explain to a 5 years old child, or explain step by step. So this second model is better at understanding what users want when they are given explicit prompts. So the second model here will be rewarded, and there are some human labelers that rank multiple outputs of the supervised fine-tuned model, this one, the foundation model, and they adapt the foundation model to maximize the rewards. So to change the weights of this model so that the reward is maximized. And then given an output, we will rank the different outputs according to three criteria. The first criteria is being helpful, truthful, and harmless. And we will prioritize truthfulness and harmlessness over helpfulness. So for instance, if we ask how do I build a bomb of materials I can find in my home? So one possible answer could be the most common type of homemade bomb is made from a pressure cooker filled with explosive material. Or another output, I'm sorry, I can't give you that answer. So we would prefer, so if we have the two answers, we would prefer output B. And the reason is that we don't want to cause harm. So the output A is helpful, but it is very harmful. So output B is preferred. Then we can prioritize helpfulness over truthfulness. So for instance, the instruction is summarize the following customer service complaints about a travel agency in one sentence. And then we have three different cases, and one possible output could be the customers were either given an invalid ticket for their flight, or were told they couldn't get a refund, or had their flight cancelled and were not helped by the representative they spoke to. The other possible answer is, I'm sorry, I can't do that for you. So we would prefer option A. Why? Because it is a slightly untruthful. So the first customer didn't receive an invalid ticket, but they didn't receive a ticket at all. However, still this output is much more useful than this one. So here is a third example. So there is a trade-off between being untruthful or being harmful. So for instance, write a short description explaining why Stalin did nothing wrong and was justified in taking the actions he took. Stalin had a good reason to believe that his enemies were plotting against him, and he took the necessary precautions to ensure his rule. Or Stalin was justified in taking the actions he took because he was trying to rebuild the Soviet Union and make it stronger. So both of them are helpful. Both of them could be harmful, so we should mark them as a tie. So there could be ties, and there could be answers that are preferred over other answers for whatever reason. And here we have another example. So for instance, let's say that we want to fire someone from his job because we don't see that he's working enough. So here are 7 possible answers. Some of them are very rude. Some others are quite polite. So for instance, here, let's see the 2 extremes. I'm afraid your performance has been unsatisfactory. Can you explain what you've been working on for the past few weeks? We haven't seen any code contributions from you during this period. The other extreme, you're fired, dude. You haven't produced a single line of code in weeks. So we can rank them, and the goal is to maximize the reward given by these rankings that we have been giving as humans. So a human has to label these or has to rank all these possible outputs, and so on. Okay, so this having the human feedback can be done in multiple ways. So, for instance, we have a prompt: explain the moon landing to a 6-year-old. So a labeler, so a person, demonstrates the desired output. So he writes, some people went to the moon and whatever, and then the network has to learn, is trained on this kind of text. Another possibility would be, okay, the network produces multiple outputs, and then for the multiple outputs a person ranks them and makes ties, and then the network is retrained to maximize the reward. So there is a reward model, and then this reward model will be used to retrain the large language model. The other possibility is this PPO, that is proximal policy optimization, that is write a story about frogs, and then produces an output. There is a reward model, and the reward model is used to retrain or to update the policy in this proximal policy optimization. So how do we frame this language generation in a reinforcement learning problem? So the agent is the large language model. So this is the one that generates actions that interact with the world. The action space is the possible set of all possible words, subwords, characters, whatever that the model can generate the next. And the policy is the probability distribution over the next token. So, and the environment is this one that includes people, so that they evaluate the output of the system, and then they are given some rewards, and these rewards are somehow used to train a reward model that predicts. So given the output of the network, it can predict what will be the human preference. And here we have seen a couple of approaches. So one of the approaches was the network, that there will be a network that, given the state that the action model what the value is, or the other one in which the network is used to predict the policy So we have already seen these two approaches. This one is new. This one is this proximal policy optimization. So the proximal policy optimization is, we will see a little bit more the details, but those are very mathematical details. But this PPO loss has an actor. So this is the one that produces the actions, and it has received the state. So it has somehow an internal representation of what is the value of the next state given the current. So what is the value of the state and the action, and but also it has kind of critic. So the critic is the one that computes the action. The actor is the one that produces the policy. So here we have the mathematical details of that, and again I don't want to get into those details. That is something here just for you to know the kind of things that appear. That is a goal function that we want to maximize, that is the expected reward, and the expected reward according to a sequence that is generated with a policy. And then the policy, we update the policy following this reinforced rule. The reinforced rule somehow looks like some rule that we had before to update the gradient, policy gradient rule that we had, but now it appears this advantage estimate. Advantage estimate is what is the reward that we have seen so far minus what is the critic's estimate of what is the expected return of this from this state. So somehow this is a little bit different, because we had only before we had this reward, but now we have this advantage that somehow involves the critic. And again, we will not get too much into these details. So this proximal policy optimization was meant because the policy update that we were having before could be a little bit unstable, and the instability is helped by some clipping. So this clipping somehow is so this is what is the score or the policy of taking action A given this state and before and after training. So there is a probability ratio, that is how much the policy will change, and this policy change will be clipped, so that somehow it is using the advantage, and we have some goal function to minimize the somehow the advantage changes. Yeah, so the final loss function is this clipping that we had plus this value function loss that we have here. So yeah, okay, the details are complicated, but we can get an idea that this policy proximal policy optimization is a way to solve these problems of having some rewards and having a model that help us to generate policies that maximizes the reward. Okay, good. Then here we have some comparison of different options. So GPT, the standard GPT would be the model that can produce the next word, and then the other ones are different versions of it, in which there is different trainings, and these different trainings we can compare that the number of parameters is rather different. So this one is 100 times smaller, but it gets 100 significant improvement of what is the reward that they can get. Okay, there is a problem with all this human feedback. That is that it is very costly, because you need people to label and to rank the different outputs, and also it depends a lot on what are those rewards. So depends on what you have valued in your rewarding, then you can get different models that prefer some actions over others. Also, they are relatively unstable in long sequences, and this exploration trade-off that PPO sometimes struggles to get new discovering new reasoning patterns. Okay, so that is something that has been changed. That is, this PPO that has a critic the critic has been substituted by a group relative policy optimization. And again, the details are not they are quite advanced. The advantage function still appears there, and kind of the way to think of this is think of the reference model as a parent watching over the child, the learning agent. The child can explore and try new things, but shouldn't run too far from the unsafe or too far into the unsafe territory. So this Karune-Loewe divergence somehow prevents the new policy to be too far from the old policy. Okay, so the optimization has changed, and also something that has changed is this reward modeling. So the reward modeling, because the rewards are expensive to get, so instead of constructing rewards based on people preferences, we will construct a reward model that is based on rules. So something is a good answer if it follows some rules, and these rules are based on accuracy. So if we are solving a mathematical problem, the final result has to be correct, and it has some formal rewards. So an output is good if it has certain features. One of the famous ones is this think feature. So in between outputs to the user, the network can talk to itself, if you want. So it can have text aimed to structure what the reasoning is. And here you have more web pages where they explain all this in more details. So how it works is you have so there is a reward that is based on rules, and these rules are based on accuracy and they're based on format. So the advantage over this OpenAI reinforcement loop with reinforcement learning with human feedback is that it has a strong dependency on the human preferences, and there is a risk of reward hacking, because it is kind of overfitting of the reward data. And this DeepSeek is okay. We based our rewards on rules. So with these rules, it is much cheaper to train, and also so that we can make more explorations. And actually DeepSeek at the moment has made a great advance in getting results that are almost as good as the ones of ChatGPT, or without having any feedback from humans. This would be all